Welcome back. This is the third video on the notion of inverse docking frequency or IDF. And in this video, I would like to present the information theoretic view. So before I get to the presentation, which is going to be brief on IDF from the point of view of information theory, I would like to present the classic information theory in a very simple way, with a very simple example, the Shannon entropy, how it is connected to the notion of information and why is that Shannon formula. So it will take another separate video just to talk about this entropy formula. But in here, I would like to first give everyone a very simple example. Hopefully it makes sense. So Shannon entropy, let's imagine you are taking a quiz, right, consisting of 3 true or false answer questions. So 3 questions, true versus false. So each one is a binary question. And so if you think of this, right, there are 8 possible answers to the quiz. So if you look at the table here, you can answer true, true, true to all the questions, or answer all false to the questions, right? And then things in between. And so if you count the number of potential choices or answers that you can give for the quiz, there are 8 different combinations. So there's 1, 2, 3 until 8, right? So there are 8 different sets of answers that you can give. And so each one is 1 out of 8. Okay, so think about this. Let me also make sure I have the annotation tool here. So what I would like to do is just to show you that, out of, give me a second. I think I need to find my cursor. And so out of, the 8 different answers, if you do not have knowledge at all, let's suppose we don't have information at all for those questions. So this is the most uncertain situation where everything has the equal probability to be chosen, right? So if you think about the first answer set, right, all true, and we can regard this as P1, right? If you have no knowledge of at all, you may just randomly pick, any answer, and so the chance of hitting all true will basically be 1 out of 8, right? So that would be 1 out of 8, okay? And then P2, okay? How likely you are going to hit the answer set 2, okay? Also 1 out of 8. This is to assume, the assumption again here is that you have no knowledge at all, right, regarding those questions. And so this is the most uncertain situation where each individual probability, okay, here regarding the answer set will be 1 out of 8. Okay, and so of course there's going to be P1, P2, P3, P until P8. So we can instead write this as PI, right? I is one of the exclusive, mutually exclusive choices that you can make here. Okay, so PI is 1 out of 8. It is an even or uniform distribution. Okay, so there are two notes I want to make here. One is that, this is the most uncertain situation where you assume you have no information at all for the questions. And so PI is 1 out of 8. So when you see 1 out of 8, you can think of that is the probability. Okay, this is first one. The second one is that I said they are mutually exclusive answer sets, right? Because these are the very different combinations that you can give. Okay, so if you select the set number 1, you are not going to select number 8, right? So you basically pick a one set, even though you make choices for each of the individual questions. Ultimately, you are picking a combination out of the 8 combinations. So that's why I said they are mutually, right? Mutually exclusive. Exclusive. Okay, so only 2 notes here before we move forward. So let's continue from here. And now, if we look at the 3 questions and we assume that 3 questions are independent, that means, they are just totally, questions without any overlap of knowledge. So if you know the answer to the first question, it doesn't mean you have any information for the second question. So if they are separate, think about this. They are true or false answers. And so you can think, maybe I need 3 pieces of information, right? Because there's no overlap of information for them. So independently, I need 3 pieces of information. And because they are binary questions, so you can go ahead to say, I need 3 bits of information, right? So here, I think 3 is the key. So therefore, the amount of information required to find the correct answer should be proportional to something like 3, okay? Which we can get to by using the probability here. Okay, so again, let me use my notation. Okay, so if we put 1 over 8, right, we can again think of this as one of those PI values. Okay, so this is a probability, right? We have a minus here, okay, because this is just to rewrite the formula here, right? This is log and then base 2, and 2 to the power of 3 is essentially 8 because we have 8 different combinations. That's the reason we need an 8 here. And the reason we choose log base 2 is because, of course, here these are binary questions, so it makes sense to use 2 as a log base. Okay, so ultimately this is the minus log p. Okay, so because 1 over 8 is the probability, so I hope it makes sense so far. Now let's move next. Okay, so from here, now, so we think we need 3 pieces of information, right, or 3 bits overall to get to the correct answer. Now, if we think of each answer set out of the 8 and we treat them equally likely, which means we just don't have the information here right now. In the case of seeking information at the starting point, we just do not have the information, and it's the uncertain situation where we just don't know which one to pick, so we can pick randomly. So each answer set is equally likely. Okay, so when we take a look at each answer set, okay, what we can kind of generalize here is that each one represents this amount of uncertainty, okay, because each one is 1 out of 8, okay, and there's a minus here, okay, so each one is 1 out of 8, okay, and so the uncertainty is represented in this log 1 over 8, okay. Now, but we're talking about 1, so this can be 1 for the PI. PI can be P1, P2, P3, until P8. And so if minus log 1 out of 8 is the uncertainty, okay, and let me write it down, just I'm hitting some button that cancels. So this is the uncertainty, and sorry for the messy handwriting, for each answer set. Okay, so for each set, right? So, and we think about the overall situation, okay, because this is an uncertainty for each set, and each set is 1 out of the 8. When we want to combine them together, each one is also proportionally contributing 1/8, okay, to the overall uncertainty of the entire system of answering the 3 questions here, okay. And so that's why we need to plug in if we want to kind of consider take into account the contribution of uncertainty from each set of answers. Okay, we need to use this pi to multiply the uncertainty for each set, because this can be viewed as a weight, okay, for each pi's or each answer set's contribution to the overall uncertainty, okay. And so if we do that and put things together, right, so pi is only just one set, okay. So this minus pi log pi, this is uncertainty for each answer set. And in order to calculate the uncertainty for the entire quiz, we need to add things together. So we need to put a sigma here, okay. And so in the end, we reach the formula for Shannon entropy, okay, which come with the sigma, right, minus pi log p. And if we plug this in formula back into the example of three true false answer quiz, then what you will realize here is that in the end, right, so we have minus pi log pi, okay, and in our case, pi is always 1/8, right? So and we sum them together, okay. There are 8 different probabilities here, okay. And so in the end, you can get a calculation. It should be a very simple calculation here, okay. In the end, you will also get to 3, okay. And this is the same 3, the intuitive answer that we have. Like, there are 3 questions, there are 3 binary questions, so we need 3 bits of information, okay, for that quiz in order to get to the correct answers for that quiz, okay. And so indeed the answer is 3, and that is kind of an example for the Shannon entropy, why this is the case. Of course, there are many more complex situations, and this is just a starting point for you at least to appreciate this equation for the uncertainty. So in Shannon entropy, uncertainty is just the kind of the reverse or the inverse of information, because I think Shannon's basic assumption is that if you introduce information, that is going to reduce the amount of uncertainty. And so by calculating the reduction of uncertainty, okay, you can calculate or estimate the amount of information in the process. Okay, so in a sense, the degree of uncertainty or the notion of entropy is equivalent to information. Okay, so I'll stop here for Shannon entropy, and now I would like to move to the notion of IDF, inverse document frequency, and to establish the connection between information theory and inverse document frequency, or IDF. Okay, so just to give you a very broad picture, a big picture of information theory and its development. So Shannon entropy was proposed in 1948 by Claude Shannon, and entropy as the amount of missing information. And Shannon basically borrowed the notion of entropy from physics, from thermodynamics study. Okay, of course, we are talking about the information, and if you apply, log base 2 in the formula, we are talking about bits. Okay, in the amount of information or the degree of entropy. So that is Shannon's entropy. Now, Shannon's entropy is really just about the property of a one probability distribution. So there's one value associated, okay, with this degree this probability distribution of a system. Okay, it does not necessarily give you anything related to two distributions. So if you want to say, okay, if I have some rough idea data that allow me to estimate the probability distribution, and I try to estimate as accurate as possible the true distribution, and I want to know how much more information do I need, or how many more bits do I need in order to accurately depict the true distribution, right? Can I do that kind of calculation? Shannon entropy unfortunately does not give you that tool to do so. But here comes the callback and liability, or KL divergence, or relative entropy. Okay, relative entropy can be thought of not very accurately as the difference between two probability distributions. Obviously, you cannot think of it as a distance, because KL divergence is not a magic distance, and I'm happy to make another video just to talk about some of the key characteristics of KL divergence. But in this video, I would like to be very, very brief. So KL divergence is just to measure. You can think of it as the difference between two probability distributions, but more accurately, it should be regarded as if you have a kind of a rough estimation of a probability distribution. It measures the amount of information that you still need in order to get to the more accurate depiction of the true distribution. Okay, so and it's an important application of Shannon entropy, which leads to many other applications. And just as a note here, because I think many people know about mutual information, and mutual information is actually an application of KL divergence. Okay, now let's take a look at what KL divergence looks like. And I want to remind everyone of the Shannon entropy formula. Okay, so Shannon entropy is normally written as an H, right? H for the entropy, and then of course it's a function of the P. P is a probability distribution. Okay, and I write capital P here, but then in the formula I'm going to say, okay, small p normally, and then I should say pi minus pi log pi, or px. whatever, okay, and then okay, so subscribe. So this is the Shannon entropy, okay, and KL, and you can see Shannon entropy is just about 1p, one probability distribution, but KL is about some kind of difference between P and Q, okay. So Q is like the rough estimate distribution that you have obtained based on your data, and Q perhaps is the ultimate probability distribution you try to estimate, okay. So and so this KL measures the amount of information that you still need in order to get to P from Q, okay. And so this is the formula. So what KL, so KL is computed by the sum of, so sigma px times log px divided by qx, okay. So I should say that P and Q obviously, okay, are about the same set of mutually exclusive choices. So in the example of 3 true-false answers questions for the quiz, you know, Q and P in this case should be about the same quiz, okay. You cannot use P for a quiz of 100 questions and Q for a quiz of 2 questions. That is not going to work. So so the reason I write X is because P and Q should be about the same variable, basically, okay. So they should be about the same variable. You just try to get from one estimate probability distribution to another, okay. So that is the formula. Now in this video I just want to show you that IDF is in fact an application of the KL divergence or relative entropy. So let's take a look. Okay, so how do we get there? Okay, so let's go back to our you know, example, right? So I think the notion of IDF or inverse document frequency really come from information retrieval or text mining. And in our discussions previously, we talked about the example of the Maid of Orleans, right? So we use the Maid of Orleans as a search query. For example, if you are searching for the Maid of Orleans on Google and you want to be able to find information, and I think we discussed, you know, it's important to identify which terms are more important than the others, right? Whether it's the or the Maid or Orleans, right? Which one term should be given more weight, and that is the purpose of IDF or inverse document frequency. So before we get there, we can use the example perhaps of Maid. Okay, so again, let me use my annotation. Okay, so let's say we are interested in the term Maid. Okay, and we want to see how much information or how much weight we should assign to the term Maid. In order to go there, let's have a thought experiment. And in this thought experiment, I'm going to have a black box. Okay, so let me draw a black box with an opening. Okay. So in this black box, this represents the collection of documents. Okay, so this on the web, this is going to be a huge black box of billions of even trillions of documents in there. Okay, but it can be any black box. Okay, but in that black box, we're going to have documents, okay, or web pages, right? So I'm just showing examples of pages or documents, right? Lots of documents in here. Okay, so I'm not going to, of course, draw all the documents here, but you get the idea, right? So lots of documents in here. Okay, now, and we can say there are N documents, capital N. Okay, N be a billion, can be 1,000 if you are interested only a small collection in your personal library. Okay, but N be a billion or trillion on the web, right? So total number of documents, capital N. Now, what we would like to do is to randomly draw, okay, a document from all the capital N documents. Okay, and our question here is that if you randomly draw a document from the N document, how likely you're going to see a document that contains the term made? Okay, that is a question. Okay, so we are going to, right, draw a document out and read the document to see if it contains this term, right? And want to estimate the probability. So how likely you are going to have that? Now, so from there, if you can run some statistics of all the documents and take a look at the number of documents containing the term made, okay? So perhaps out of 1 billion documents on the web, there are 1 million, okay, that contain the term made, okay, and we use NT, okay, to denote the number of documents containing the term T, okay, and in the case of made, maybe NT is 1 million, okay. And so in order to answer the question how likely you are going to draw a random document containing term T, right, that probability can be computed by NT, which is the number of documents containing the term T divided by the total number of documents. I hope this makes sense. Okay, and we use QT to denote this probability. Okay, so again, in this case, QT is the likelihood or probability that you are going to see the term made or T in a randomly drawn document from the entire collection. Okay, so this is QT. There is also the QT prime, which we use to denote the complementary probability, which is like opposite. How likely you are not going to see the term T in the drawn document. Okay, so that is basically 1 minus, right, NT divided by capital N, right? And so that is going to be, okay, this formula here. Okay, so we have the QT and QT prime. They are mutually exclusive. Think about this. QT, right, the chance, the probability you're going to see the term. QT prime, the probability you are not going to see the term, right? They're complementary, they are mutually exclusive. So QT and QT prime construct a binary probability distribution. It's a discrete probability distribution, but it is a distribution, okay? To see it or not to see it, right? So QT. Now, and then let's go next. Okay, so we have QT, and which can be part of the KL divergence, but allow me a second to go through. Now, we have QT for the Q, okay? What about P? What is P here? Okay, so we have already have Q here, okay? For the collection of documents concerning, again, a particular term such as made, okay? So we do not want to lose sight of what we are doing here. Okay. Now, let's say we are already reading a document. Okay. And in this particular document, we're reading it and we see the term made in it, okay, as part of the descriptions and perhaps the article that we are reading right here. And so if we see it, okay, this is the actual result, right? We're reading the document with the term made in it. So in this case, what is the likelihood that you are going to see the term? Okay. So in this case, because you already see it in the document, it's certain, and the probability is 100% or 1. So the probability distribution here is that with PT is 1. Okay. So because you see it, it's certain, it's 100% there. And then PT prime, the probability that you are not seeing it is 1 minus 1 equal to 0. Okay? So in this particular P distribution, the complementary probability is PT versus PT prime is 1 and 0. Okay, so we have Q from the previous discussion. We have the P for this particular distribution when we see the term, right? So the amount of information from this random drawing to actually reading the document with the term, we can compute the KL divergence. Okay, which is going to be, according to the formula, is the sum of PT or PX or P whatever, but in this case we're going to say PT times log PT divided by QT. Okay, and there are two parts because it's a binary distribution. Okay, there is the PT and QT, there is PT prime and QT prime, and if we plug all the values in, okay, PT, as we know in this case we are seeing the term, so it's 1 times 1 divided by QT, which is the probability of seeing the term in a randomly drawn document, which is NT divided by N. Okay, and then the complementary part, because PT prime is 0, so we actually don't care because this part is going to be 0 anyway, so we can focus on this the first part, which turns out to be log N divided by NT, and this is exactly IDF. Okay, so the inverse docking frequency for this particular term T, such as the term made, okay, is actually the application of the KL divergence, which is the amount of information of the term. So how do we interpret this? Okay, KL divergence is basically the relative entropy. Is a way to say how much information do I need in order to get to that distribution. Okay, so in the context of text mining and information retrieval, we can basically say that the IDF of a term T is the amount of information that the term carries when you actually read it or you actually see it in the document in the context of the entire collection. So if you're searching on the web and you are reading a document containing a particular term such as made, okay, the amount of information that the made gives you can be computed by its IDF or inverse document frequency in the context of the entire web. I hope this makes sense, and I hope this also gives you a new perspective on the notion of IDF or inverse document frequency. And I hope to see you in the next video. Bye for now.